With this video, I'm going to talk a little bit about how chemists use stoichiometry to get between species and chemical reactions. Okay, so when we're looking at a chemical reaction, and it could be even something as simple as a combustion reaction, where maybe we're taking methane, CH4, methane gas, so that's natural gas, reacting it with oxygen gas, it's probably occurring in your furnace, and we're making carbon dioxide, CO2, and water, H2O. All right, and these are going to both be likely in the gaseous form. We'd make sure we want to balance this equation first. So how many of each of these do I have? Let's quickly balance it. I've got one carbon. I've got 4 hydrogens. I've only got 2 hydrogens over here. I've got only 2 oxygens over here, and I've got 3 oxygens over here. Oh, bit off so much more than I can chew. To balance the hydrogens first, I'm going to throw a 2 in front of this species. So my hydrogens are now balanced. I've got 4 on each side. That changed my oxygens up to 5 oxygens, right? Because I've got 2 from here, and 4 oxygens. I've got 2 from there and 2 from there. I've only got 2 oxygens on this side, so let's put a 2 in front of there, and I think that'll do it, but let's go through and do one final check. Let me just get rid of all these little dots. So let's see. I've got 1 carbon, 1 carbon. I've got 4 total hydrogens. I've got 4 total hydrogens. I've got 4 total oxygens, and I've got 2 oxygens from here and 2 oxygens from here, so that's 4. So there we go. Woo! Quickly balance that chemical equation. All right, so put that in the center. Stoichiometry allows us to convert between any of these 4 species using the coefficients in front of those numbers. So here's what I'm saying. If I'm saying for let's think of this in terms of molecules. I need 1 molecule of methane gas. So that's carbon with 4 hydrogens on it. So hydrogen, hydrogen, hydrogen. To react with 2 oxygen. So that's O2s, right? Maybe I'll color that. So 2 of those, 2 molecules. So these coefficients even let us know how many molecules we need of everything. And I'm going to get 1 carbon dioxide and 2 molecules of water. H and H and H and H. Okay. So look, we have 4 oxygen atoms, 1, 2, 3, 4 oxygen atoms. I've got my 4 hydrogen atoms, 1, 2, 3, 4, and I've got my 1 carbon atom here. So you can see that 1 molecule of methane plus 2 molecules of O2 gives me my 1 molecule of CO2 and 2 molecules of water. All right, so if I told you though, hey, I've got 8 molecules of oxygen and an excess of methane, how many molecules of carbon dioxide could you make? So this is where stoichiometry comes into play. So if I told you I have 8 molecules of oxygen, right, and I have excess methane, so you don't have to worry about methane, there's just an endless supply, let's say, how many total molecules of carbon dioxide would I make? Well, you look at our balanced equation, you say, hey, look, for every 2 molecules of oxygen, I only make 1 molecule of carbon dioxide. So when we set up our dimensional analysis, I can say, hey, for every 2 molecules of oxygen, I only net 1 molecule of carbon dioxide. Notice that molecules of oxygen cancel. Now, I've also purposely subscripted molecules in the form of mole here because they're the same thing. Moles and molecules, right? 1 mole is just a lot of individual molecules. It's Avogadro's number amount, right? So when we're talking about moles of things, if it helps you to think of moles as molecules, then do it, because it makes a small amount of mathematical difference because it's not a number that's 10 to the 26th, but as far as like abstract thinking wise, it's the same thing, okay? So back to my original question, if I had 8 total molecules of oxygen and an endless supply of methane, I could only make 4 molecules of carbon dioxide, right? Because 8 divided by 2 is 4. So this is how stoichiometry is going to play out a lot. But the thing is that usually, I mean, some of your homework questions and some questions you can find in the back of the book are that simple, where it just talks about you converting moles to moles and you don't have to think too much about other things. But here's where we have to think back to what we covered in class last week. So remember, if I want moles of something, and I'm going to say moles of A, okay, moles of A. But what if you're given grams of A? So what if you start with the mass of A? How do you convert between mass and moles? There's something that you need in order to always convert between mass and moles, and that's going to be the formula weight, right? Because remember, it even has units of grams per mole. Mass, moles, that's how you can get between the two. What if you are given the volume of something, so volume of A, and you need to convert to moles of A? So if I was given the volume of A, there's two things I could do. There's two values if you're given the volume of something. You either maybe know it's a mixture, and so it has a molarity, like you've dissolved some of it in water. And so you could use molarity of A, and remember that's moles over liters, so moles in volume. Or the only other volume liquid type property that you would have is the density of something. So density, which is in grams per mole. Sorry, grams per milliliter. Geez Louise, grams per milliliter. Okay. So if I'm given the volume of A and I need to get to moles of A for whatever reason, I can convert, it depends. Again, is it a solution or is it a pure substance? If it's pure, they're going to give you the density. If it's a solution where it's dissolved in something, they'll give you the molarity. But let's say it's a solution. So if I have the volume and I know the molarity, I can get to how many moles of A I have. Maybe the last thing would be the number. What if they tell me I have this many number of atoms of A? How do I convert that to moles? This is just, you have to use Avogadro's number, Na. So that's 6.022 times 10 to the 23rd is what you'll have to use. And by A, I mean any one of these species of the four in your equation. So A just denotes like one of the species in your chemical equation, okay? If you are given A, like, remember when I told you I had 8 molecules of oxygen, but how many CO2s can I make? So in that example, oxygen, I'm going to call my A, and my B, it would be what I'm going to, that would be my CO2. Okay. But to convert between moles of A and moles of B, you have to know the stoichiometric factor. And that's a big, messy word for saying you have to know what the coefficients are, right? Because the coefficients end up telling you like the ratio of how much you need. So for every it's a 2-to-1 ratio. For every 2 of these, I get 1 of these. So it's 2-to-1. And that's the same thing as saying the stoichiometric factor. So you might even say stoichiometric coefficients. Okay. And that gets you to moles of B. Once you're in B, right now, let's say, so where did I start on that last one? Let me get my highlighter here. So the last one, when I gave you that thing, I said, oh, I had this many number of molecules, right? I said I have 8 molecules of A. So if I wanted to really do it, I would convert molecules to moles through Avogadro's number. Then I would convert moles to moles of B, which B was my CO2 in this case. But then maybe it can ask you, instead of just stopping at moles of B, maybe it'll say, hey, how many grams of B is that actually? So on the B side, you can do pretty much, you can mirror everything that's over here from the B side, right? If I'm given moles and they want me to get to grams of B, right? What do you need? You need the formula weight, or the formula mass, sorry. The formula weight, right? Which is in grams per mole. But that time you're looking at the B compound, right? So I need the formula weight of CO2, and that could get me to grams of B. If they tell you what the molarity is for B, you could get to the volume of the solution you need. Or maybe they want you to figure out the volume through the density, right, which is in grams per milliliter. You could also, maybe they wanted to say, hey, how many number of molecules of B could you make? And you could do that too. You would just need to have Avogadro's number. So I'm going to erase this so you can kind of see. So here's the big takeaway for conceptualizing how to go about a lot of these chemistry problems is You're just looking at this type of a diagram, which seems scary at first, but it's really not that hard. And you could easily write this and draw this down. All this chapter 4 is really introducing. So remember, we've done this. This was all chapter 3. This molarity was chapter 3, densities, even probably earlier than that, formula weight was chapter 3. So we've done all those. The new thing that this chapter is giving us a way to convert between 2 different chemical species in one chemical equation. And that's through these stoichiometric coefficients, which is just the coefficients of the balanced chemical equation. All right, so come on Thursday, I'll work a lot of problems for you, but this is the general concept you need to be thinking about. Like, you should come kind of with this map in your mind.